Okay, this guy is fascinating. Born in 1908, and he was one of the Martians, the Hungarian scientists group that did so much uh, toward bringing the Manhattan Project to fruition. Um, but he went beyond that, and he ran into a lot of opposition from Oppenheimer, and I think even Fermi had some concerns, um, but and he was a very abrasive personality, so he didn't get along very well with a lot of people. But an interesting person, and came up with the idea of using the fission bomb to initiate the fusion bomb. Um, along with a guy named Ulam, who we'll talk about as well, and also with John von Neumann, he came up with the idea of the using the Monte Carlo method, which we're going to talk about it in some detail. Um, First we'll talk about mass deficit and energy a little bit, talk a little bit about binding energy fusion and the design of the hydrogen bomb, how it operates, show you an old slide about comparing it to the A-bomb, and then talk about the Monte Carlo method. He was born in Budapest. He earned this thing is a little bit too big for the screen. Let's see if I can shrink it a little bit. There we go. At the age of 22, he earned his PhD. So when I was 22, I got my bachelor's degree. So that's quite an accomplishment. He studied under Heisenberg of uncertainty principle fame. He looked at the hydrogen molecular ion. He spent 2 years at Göttingen. He left in Germany in 1934, along with a lot of other scientists. Moved to Copenhagen and worked with Niels Bohr. And in 1934, he got married. In 1935, he came to GWU downtown and worked with a guy named George Gamow, who will be the subject probably of a future lecture. He was a theoretical physicist and cosmologist and an early advocate and developer of the Big Bang Theory. This is a picture of Gamow here. So we'll talk about him in more detail another time. In 1941, Teller became a naturalized citizen of the United States and started working on fusion and fission bombs. This is kind of interesting. These 17 Nobel Prize winners all fled Germany. Most of them are Jewish, but not all of them. And they were all concerned about the rise of Hitler to power. And in 1933, Hitler became the Chancellor of Germany, and they all left. There are probably some others, of course, that left, like Szilard, who didn't win a Nobel Prize but made significant contributions. So I think it's safe to say that at least 20, maybe 25 very influential scientists left Germany because of Hitler's rise to power. This is a book that was written, Hitler's Gift, Scientists Who Fled Nazi Germany. Had they not left, who knows who might have had the atomic bomb before us.
What's the author's name of that book?
There are two authors, Medawar, Medawar, and Pyke, Pyke. In 1939, he came up with a guy, collaborating with a guy named John or Jan. How do you pronounce it, Stuart? Jan. Okay. And looked at the distortion of electron clouds in certain situations, refined the concept of superconductivity, which is very important because it turns out that when you can cool a metal down to very, very low temperatures, near absolute zero, the resistance of that metal to electrical current virtually disappears. So this became and is very important in high-speed computers, and allows them to operate at much higher speeds. In 1942, he was invited to start working at UC Berkeley for the origins of the Manhattan Project, working with Oppenheimer. First, he started with Szilard at the University of Chicago, and then he moved to Los Alamos and became obsessed with the hydrogen bomb, and that caused a lot of tensions with other scientists, particularly Hans Bethe, the division leader. So he had a lot of conflicts there. In 1943, he was recruited for Los Alamos. He worked with Oppenheimer and on the fission bomb, but he began to digress to focus on his interest in the fusion bomb, potentially more powerful than the fission bomb, and eventually was removed from the project because of his disagreements with the project's leaders. This is a picture of Oppenheimer. He left Los Alamos in '46 after the war, and he helped initiate the Livermore lab. I put this slide up because I didn't realize how large the facility was. You can see there's about 20 buildings in the Livermore lab. So it's a very large facility, and Teller was instrumental in getting it started. And part of the reason he did it was because of his disagreements with Oppenheimer. So they went into competition with Los Alamos. In 1950, Truman ordered the development of the hydrogen bomb. And Teller continued to work on it. In 1949, the Soviet Union successfully tested an atomic bomb. So that gave impetus to Teller's work on the hydrogen bomb. In '51, he collaborated with Ulam, ULAM, and formulated a successful configuration. It was hard for Teller to even theoretically show how you could get the fusion reaction started. And Ulam came up with the idea of using a fission bomb, and we'll talk more about the construction of the H-bomb, in order to get that fusion reaction started. Between 52 and 75, Teller worked at Lawrence Livermore. He served as associate director from 54 to 58, and from 60 to 75. And as its director from 58 to 60. So he was very instrumental in getting Lawrence Livermore started. Here's a picture of Truman, of course. And when I was a kid, I think it must have been around 1950. So I was 12 years old. I saw a parade, I think it must have been in New York City. And I was about 10 feet from Truman. Got pretty close to him at that time. The Secret Service wasn't too fussy. In '49, ironically, Oppenheimer, following kind of the pattern that was set by many other scientists like Einstein, he became a pacifist, and he declared the hydrogen bomb to be dangerous and immoral. He didn't mention the atomic bomb, but the implication was clear.
I think he was guilty about the atomic.
Oh yeah, he was guilty about it.
Yeah.
Yeah. Okay. And so then Truman ordered the development of the hydrogen bomb in 50. In 52, the first hydrogen bomb was successfully tested at Inuiatak Atoll in the Pacific Ocean. In 54, the U.S. government heard testimony regarding Oppenheimer's potential security risks. The FBI was very leery of him and Einstein and many other scientists who became pacifists. Teller actually testified against Oppenheimer. He said, "I feel I would prefer to see the vital interests of this country in hands that I understand better and therefore trust more." And that isolated him from a lot of other scientists because of his criticism of Oppenheimer. And they did revoke Oppenheimer's security clearance at that time. This is a picture of Inuiatak Atoll. It's kind of interesting. They kind of cemented over the test site to try to contain the radiation, I guess. The island itself looks like this. It's a very long, thin strip of land. The test was done right at the end, at one end of the island. I'll give you a chance to read that a little bit. The government gave initially $150 million in 1983, which is probably like maybe half a billion now, and it was later revised upward to 244 million in the year 2000, and they've tried to replace the irradiated soil on the island. Apparently people live there or nearby islands. In 1955 to 2003, Teller continued to be an advocate of a strong defense policy. He was involved with the Star Wars, the SDI project that Reagan initiated, and was a strong proponent of that. He got a Presidential Medal of Freedom in 2003, a few months before he died, in 2003. So this talks about NORAD and Reagan's use of the SDI project to try to stop long-range ICBMs. Dr. Teller told Reagan in a letter in 1982, because of the potential of these new types of nuclear weapons, this matter is the most important one in strategic military affairs since the advent of the hydrogen bomb. And he asked for $55 million to do the project. So the only reason I put this slide up, it kind of repeats a lot of the things I've said already, but I wanted you to see that he was possibly the model for Dr. Strangelove, or How I Learned to Stop Worrying and Love the Bomb.
It's Platinum Cheney too.
I remember seeing that movie, yeah. This is a picture of Kennedy giving the Fermi Award to Teller. This Glenn Seaborg, who at that time, I believe, was the chairman of the Atomic Energy Commission. This is Mrs. Teller.
That was in 1962.
62, yeah. So that was like about 3 years before I met Seaborg. So I'm pretty sure at that time he was the chair of the AUC. That's why he was in the presentation ceremony. All right, so let's talk a little bit about the science behind the bomb. We've already talked a lot about this, that because C squared is such a large number, that a very small mass can produce a lot of energy. Okay, the actual hydrogen bomb uses deuterium and tritium combination to form helium, energy, and a neutron that can be used to produce a chain reaction by hitting another another hydrogen atom, forming the deuterium and the tritium that are needed for the reaction. Just to give you an idea, 1/millionth of a gram of mass of energy would release approximately 90 million watts of power. 1/millionth of a gram. So 1 grain of long grain rice weighs about a 64th of a gram. It varies, slightly. So that's 15,625 micromillionths of a gram. If we converted that every second, it would produce about 1.4 trillion watts every second. New York City uses about 458 million watts every second. So 3 New York City-sized cities could be powered by 1 gram of rice, totally converted into energy per second. Amazing amount of energy from a small amount of material. To find the mass deficit of a nucleus, it's the difference between the mass of the separated nucleons and the combined mass of the nucleus. Okay? So the mass deficit can be found by simply multiplying these quantities by c squared and find the energy deficit, so to speak. And we have to talk about binding energy. So in a nucleus, we know that the protons are going to repel each other because they have the same charge. Okay? So they're trying to push the nucleus apart. Okay? The binding energy of a nucleus is the energy per nucleon of a nucleus divided by the total number of nucleons. As a measure of stability of the nucleus, the larger the binding energy per nucleon, the greater the amount of work that has to be done to remove the nucleon from the nucleus. So you got the protons pushing the nucleus apart. You got the nuclear forces. There are 2 types, strong and weak, that are holding the nucleus together. Okay? So when you have a balance between those forces, the nucleus is stable, and you have to apply energy to it to pull it apart. Okay? It turns out that if you take the individual constituents of the nucleus, neutrons and protons, and you add up their mass, the sum of all that mass is always going to be greater than the total mass of the nucleus. Okay? So when you put these together in a nucleus, some of that mass is converted into energy. And that's called the binding energy. It's also, you could also consider nuclear binding energy is the amount of work that has to be done on the nucleus to separate it into its constituent parts. Okay? So if you take that mass of the nucleus and multiply it by c squared, you get energy. plus the binding energy, and that equals the mass of the individual particles times c squared. So energy is going to be released when a nucleus is formed from its constituent nucleons. So when you put two hydrogen atoms together, basically, to form helium, you're going to release energy. Okay? You've seen this chart before. It turns out, and it's hard to read, so I'll read it to you. This axis here is the binding energy. We have hydrogen down here. Helium is here, okay? So there's a little bit of difference between the two. Uranium is over here, okay? And so you can see that when you break an atom apart, okay, there's a very slight increase trend in binding energy, in the release of energy. Okay, things become more stable in this direction and in this direction. The greatest stability is reached right around iron, which is up here. Okay, so the degree of the region of greatest stability is right in here. Now, in nature, things tend always to go to the region of greatest stability. Okay? So where the binding energy is greatest, the atom, the nucleus, is most stable. In other words, it takes more work to pull apart an iron atom, nucleus, than it does to pull apart hydrogen or uranium. Okay? So there's a tendency for elements at the extremes to transform themselves into other elements. Okay, does that make sense? Okay, so the most stable element basically is around iron. It's kind of interesting. Nuclei with a very low or very high mass number, very low mass number would be hydrogen. A very high mass number would be like uranium, have less binding energy per nucleon and are less stable because the lesser the binding energy per nucleon, the easier it is to separate the nucleus into its constituent parts. Make sense? Nuclei with a low mass number like hydrogen may undergo fusion. Okay? So in order to get rid of that, in order to satisfy that instability, they will combine with other elements. So hydrogen, we know hydrogen combines very readily with other things, very explosive, right? So hydrogen will tend to combine with other elements chemically to form other molecules. Water is a good example, okay? And the nuclei of hydrogen will combine fairly readily with other hydrogen in order to form higher binding energy elements. Okay? Nuclei with high mass numbers, like uranium, may split apart in order to try to become more stable elements, like iron. Okay? So the tendency for uranium out here is to move toward iron. The tendency for hydrogen down here is to move toward iron. The operation of the hydrogen bomb was in these 5 steps. First, step A, the warhead before firing has a primary initiator at the top. Okay, and both of these components are fusion boosted fission bombs, okay? So they're both atomic bombs, basically. The second step, a high explosive fires in the primary, compressing the plutonium core, and it becomes critical and begins a fission reaction. In other words, an atomic bomb goes off here. In step C, the fission in the primary emits X-rays, which channel along the side of the casing and irradiate the polystyrene foam channel filter. The polystyrene becomes a plasma, and a plasma expands rapidly and compresses the fission, the secondary fission bomb, and inside that bomb there's a plutonium spark plug, they call it, okay? And that begins to supply heat. Now heat, remember, the quality of heat or temperature is a representative of the speed at which the molecules are moving. Now, as the speed increases, the molecules of the lithium deuterium fuel that's in the bomb begins to heat up and it begins to fuse. The fusion reaction begins. In the uranium bomb, we needed to get enough, or in the fission bomb, I should say, we needed to get enough material to go critical, okay? And it was hard. It was hard to produce that material, as you saw from my previous lecture. It took a lot of work to get enough material together to make a bomb. Hydrogen bombs, fusion bombs, the material was something called lithium deuteride. It was easy to make a lot of it. So the difference between the two bombs is that the explosive power in the atomic bomb was limited by the amount of material that you could get together. In the hydrogen bomb, you get a lot more material together. So even though the initial individual reaction didn't produce as much energy, because you had so much more material in the hydrogen bomb, you got a lot bigger explosion. Finally, compressed and heated, the lithium-6 deuterium fuel began the fusion reaction. Okay? And a fireball started to form in the final step. This is kind of the structure of the bomb. Okay, not much more I can say about that. I've already said this was the primary, this was the secondary. This rod here was the plutonium spark plug. And the casing confined the X-rays by reflection to the bomb itself. I already showed you this. So we know that the first hydrogen bomb tested by the US released about 10 million tons of explosive power. The first atomic bombs that we used were in the 15 to 20,000 ton range. So the hydrogen bomb was about 500 times more powerful. Okay, this just shows that in uranium, in the fission reaction, you get about 173 million electron volts of energy. So from 1 gram of uranium, you can get about 173 million electron volts. And there's the reaction. Uranium becomes barium and krypton and 3 neutrons, more or less. sometimes, actually, sometimes a little bit less than 3 neutrons. So the average, I think, was 2.4, yeah. Okay? So that's what happens with uranium when it's struck by a fast-moving neutron. The U-235 becomes U-236, and the U-236 decays into barium, krypton, 3 neutrons, and the release of 175 or 177 million electron volts. Those neutrons, of course, those extra neutrons then hit other uranium atoms and produce the chain reaction. In fusion, you only get about 1/10 as much energy. Okay? So a fusion reaction doesn't produce anywhere near as much reaction. However, because you have so much more fuel in the hydrogen bomb, it's easy to have 100, even 1,000 times more fuel. You can get a lot more energy out of a hydrogen bomb. The deuterium combines with tritium. It produces a neutron, so you get your chain reaction, and it produces helium-4. So here you see the difference in mass. The fission bomb has a mass deficit of about 2.3 atomic mass units. The fusion bomb has only a difference of about 1 atomic mass unit. So it's less than half as much energy available. But by carrying large quantities of hydrogen fuel, the greater number of reactions in a nuclear bomb, a fusion bomb, drives its force from the kiloton range, common for atomic bombs, to the megaton range, million-ton range, that has made nuclear weapons, hydrogen bombs, some of the most powerful devices. Here's where an atomic mass unit is, if you're interested. It's based on the unbound neutral atom of carbon-12. So carbon-12 was used as a standard of the atomic mass. So we say the carbon-12 is 12 atomic mass units. And then took the ratio of the other elements to carbon-12 to figure out what the atomic mass unit is. The reason I find this kind of interesting is I learned some new words. A yoctogram, a zeptogram, an attogram, a femtogram, picogram I've heard before, nanogram. But these others are very, very small quantities, okay? So I thought that was interesting to show you. And then in multiples, a yotogram, a zettagram, an hexagram, pentagram, teragram, and so on. So you'll have that in the slides when you get it. You can increase your vocabulary. You can amaze your grandchildren or children with some of these words. I don't even have a yotogram of money. Let them look it up.
You're not alone.
Just don't let the IRS find out.
Yeah, right. Now, by the way, what happens in a hydrogen bomb is not what's going on in the sun or stars. There's a different kind of fusion reaction there called the proton-proton chain. The nuclei of elements heavier than hydrogen are held together by strong nuclear forces, and that's much stronger than electromagnetic forces. But they only exist over very short distances, around the size of the nucleus, okay? To start nuclear fusion, the nuclei must somehow be brought to very close together. In the sun, it's achieved by gravity, okay? So the tremendous mass of the sun creates a very strong gravitational field, puts tremendous pressure on the core of the sun, and forces those atoms, those nuclei together. Okay? A hydrogen bomb is the two-stage weapon that you've seen. First, you have an atomic bomb, and that causes the fusion to start. The temperature created in a hydrogen bomb is about 20 million degrees Fahrenheit. Huge amount of heat. And it's that heat that burns everything. It just burns everything. In the sun, the main fusion process results in 4 hydrogen nuclei, which consists simply of a single proton combining to make a helium nucleus. 2 protons and 2 neutrons. The heavier hydrogen isotopes of deuterium and tritium, with 1 and 2 neutrons respectively, are created at intermediate steps. It's impractical to try to replicate the whole process starting with ordinary hydrogen, but the fusion of deuterium and tritium can be achieved. So an early test involved using these gases in liquefied form. But if you're going to keep these in liquefied form, you've got to refrigerate them. And that's difficult to do with a bomb, right? You can't send a refrigerator along with the bomb. Okay? The huge hydrogen bomb that the Russians exploded in Arctic had to be refrigerated because it used liquid fuel.
Was this the 100 megaton bomb?
Yeah, with the Tsar Bomba. Yeah.
Okay.
So it was the first US bomb.
But in the hydrogen bomb that we have now, and I have a picture of it later. The lithium fuel, the lithium deuteride fuel, is a powder. It's a powder. You can pack an awful lot of powder into a limited space.
In the first hydrogen bomb we built set off, it was actually a building. We built a building to house it.
You refrigerate it, I guess.
Instead of an actual bomb.
Yeah. So this goes into binding energy again, but I've already said this, okay? You got a tremendous amount of energy. Let me skip through here. The first time the principle of a hydrogen bomb was tested was on the 9th of May, 1951, during a George test of Operation Greenhouse at the Pacific Proving Grounds. Most of the energy yield came from fission fuel, but it was demonstrated that this fission bomb could be used as a stepping stone to something even more destructive. So on the 25th of May, 1951, IV Mike was tested. Oh, I'm sorry. IV Mike was tested on 1 November, 52, at Inawita Atoll. So I showed you a picture of it. The bomb exploded with a force equivalent to 10.4 million tons of TNT, which was over 450 times more powerful than the atomic bomb dropped on Nagasaki. It used liquid deuterium as fuel and required 18 tons of refrigeration equipment.
Wow.
Something that could never be carried on a missile or a plane, effectively. It wasn't a practical weapon, but it proved that a fusion bomb of enormous power could be built. A later test, called Castle Bravo, used solid lithium deuteride instead. It decreased the weight of the device, it removed the need for refrigeration, and it made it a weapon that could be carried by a plane or attached to a missile. This Castle Bravo had a yield of 15 megatons, 15 million tons. Big Ivan, the Tsar bomber, was a 50 million ton explosion, resulting in an area of complete destruction with a radius of 15.5 miles. Everything was totally destroyed.
Also, was that flying refrigeration equipment?
I'm sorry,
This is,
what was the
You
question?
said that the Bell bomb required a refrigeration plant?
I think so, yeah, I
So
think
was
it did.
that all flown at
Yeah.
13,000 feet?
And broke windows 559 miles away.
Wow.
The fireball went to a height of 34,000 feet, or about 10,300 meters. A mushroom cloud reached 210,000 feet, and the flash was visible for 621 miles. Here's a picture of lithium deuteride, okay? And you can see it's just a white powder. And that's what they pack inside this secondary part of the hydrogen bomb. So you can pack an awful lot of it in there. And that's what gives the hydrogen bomb its tremendous power. Oh, you've seen this before, okay. This is the Tsar bomber. The mushroom cloud itself could be seen from 99 miles away. If this were exploded over Paris, it would destroy, let's see, somewhere up here is London. Anyway, you can see it's a tremendous range. The weight of the bomb was 27 tons. It was detonated at some altitude. By the way, when you detonate a bomb, not at ground level, but above ground level, it has more destructive power because it's not interfered with by ground objects. So most of the surface to ground, surface to surface missiles that the U.S. Army uses are set to detonate at some altitude above the ground because the range of destruction is much greater.
You get the reflected wave,
Yeah, you get some reflection.
and that's what enhances the effect.
Right. This was equivalent to an earthquake of 8.1 on the Richter scale.
Wow.
So they actually got the thing up in the air and dropped it?
Yeah, yeah. Must have. Yeah, it was carried by a plane, yeah. I've seen a picture of a plane carrying it. So apparently it did not need refrigeration. Yeah.
Well, they said in the previous slide that there was refrigeration, and a lot of that weight was refrigeration.
Well, our early ones, yeah.
Our early one,
Yeah.
not the Soviet one.
Yeah. So they must have used lithium deuteride, or something like it, yeah.
The first Russian bomb was actually carried on a plane. It went all the way from
Yeah.
design to something that was a serviceable, carryable weapon.
Oh, yeah, I mean, I have a picture of it somewhere here. Where did I think earlier I showed you a picture of it, didn't I? I'm not sure.
They steal our plans, or did
But yeah, it fit on a plane, yeah.
they steal our plans, or did they do
No,
on their own technology?
I don't know.
they did not steal our plans. They were ahead of us on that.
I'm sure that, you know, I've heard stories like about Werner von Braun sitting in some alpine retreat with two sets of orders. One said go west, the other said go east. So he sat there, and fortunately the U.S. Army got to him first, but the Soviets weren't far behind.
Well,
So they must have captured a lot of German scientists.
well, the Germans didn't like the communists much.
No, that's true. but they didn't like the US that much either.
Well, it was a question of who was worse.
Yeah,
The Russians basically captured all the facilities.
yeah,
The-
yeah,
The Americans got all the facilities who could escape.
yeah,
The US got the brains.
yeah. Okay, so that's the Tsar bomb.
The bomb itself was actually developed by Zakharov.
By who?
Zakharov,
Sakharov,
yeah, he was the one who actually
Yeah.
developed it, and they had it to go up to 100 megatons, and he backed it down to 50, because he was scared of what it would do.
Yeah, yeah.
And then he went on to become against all wars.
Interesting. Okay, so let's talk about the Monte Carlo method. That's all I'm gonna say about the actual hydrogen bomb, although because Teller and Ulam, Teller and von Neumann came up with this method to use to figure out how to build the bomb, we would not have had the bomb. So what they found was that there were so many nuclear reactions occurring in the bomb that they couldn't reduce what was going on to a series of mathematical equations. It was a very complicated situation. And so what they did was they came up with what they called the Monte Carlo method. They called it the Monte Carlo method because it used random numbers, okay? And what they would do is they would put in random values, okay, into the situation and see what happened. I've got some examples of this that I'm going to show you, but I want you to understand what this method is. So that's the goal for the last part of this lecture. So here is a short program I wrote, which is designed to determine, which one is this? Let's see. Yeah, the value of pi, okay? So you can see that it puts random values in and determines the looks like the distance, and comes up with this value. All right, well, it's 100 times pi, right? 100 times pi. So it starts out being quite far off and gradually approaches a value that is very close to the actual value of pi. Business managers who find that projects always seem to run late, cost overruns are too common, actual results are not even close to projections, may sometimes feel like using methods akin to an atomic bomb. The Monte Carlo method was invented to solve key problems in developing the atomic bomb in the 1940s. So during World War II, von Neumann, Ulam, and another guy named Metropolis, working intensively on the Manhattan Project, had to model what would happen in a chain reaction in highly enriched uranium. And they couldn't afford to have actual results depart greatly from their projections. But this neutron diffusion model was too complex to describe and solve with algebraic equations. So the scientists had to resort to numerical methods, basically plugging many different numbers into the equations and calculating the result. Their first computers were actually people, using calculators and IBM punch card machines. Later, they were able to use electronic computers like maniacs. So they chose numbers randomly, plugged them into the equation and calculated the results. Now, they can only test thousands rather than trillions of combinations, but once they were able to get enough data, like I did here, once I had enough data, I came very close to the actual value involved. Okay? So once they got that, they were able to understand what was going to happen in an actual bomb. Here's the problem. These are just some of the reactions that are occurring in a hydrogen bomb. So it gets to be a very complicated situation. Okay? Here you have two hydrogen atoms combining to form helium-3, two hydrogen atoms forming hydrogen-3, tritium, and more hydrogen. Here, deuterium and tritium forming helium. And here, deuterium and tritium forming helium and hydrogen. So it was very complicated. And to try to write down all the equations and solve them all was impossible, because they didn't know what percentage of the time one would occur versus the other. So early, I'm sorry?
For that previous slide, how did they know those reactions? What that should go with?
How did they know? They didn't. They were theorizing that these things would occur.
Oh, that was based just,
And that was the question. In other words, you take a random number. Let's go back to maybe this is the best way to explain it.
So by using the conservation of energy and assuming that one particle.
Yeah, yeah.
They just brainstormed all those equations, not knowing if they would really actually happen.
Or what percentage of the time?
Right.
That was, the random number was the percentage.
Right.
Okay? Oh, let me give you, I got a better example. Years ago, I wanted to make investments in what are called exchange-traded funds. Now, I knew that the real problem is when you make investments that you're going to have a losing year. Because if you have a losing year, it takes a long time to recover. So looking at the closing prices on these exchange-traded funds, month by month, over a 10-year period, I said, I wonder how much money you should put into each fund. Now, some of the funds would go down while others would go up. So they were balancing each other out. So obviously, if you put the same amount into each fund, you're not gonna make any money. So I asked the question, how much money should I put into each fund, okay, at the beginning of this 10-year period, so they never have a losing year? Now, I couldn't write an equation for it, okay? It was too complicated. I mean, all sorts, the price of money, all sorts of economic factors involved. So I said, well, I'll just put random values, percentages of the total amount I have into each fund. And I'll look at the results so that I never have a losing year. When I started out, I had losing years. And I kept running the program over and over again with different numbers. And eventually, I came up with percentages that would give me a winning year every year. That's what they were looking for, okay? They were looking for the maximum amount of energy, okay, assuming certain percentages of these things would occur. And then they figured out the geometry, how much fuel, how to shape the bomb, and so forth, so that they would get that percentage of reactions.
Yeah. But they had a criteria for minimizing the number of variables. But in your case, you don't have any way of doing that. You don't know, you can't minimize the number of variables.
He just had, what was it, how many stocks that you had? How many
That's
funds
why
that you
it
I
had?
had seven different funds.
So
Right.
you only had 7 funds.
Yeah.
I mean,
Yeah.
when you
It
did
worked for them
percentages,
because they
could
could isolate the variables.
Right.
If they had the conservation of energy, things
Yeah.
like that, you didn't have anything like that.
Yeah. All I had was the closing prices.
Right, right.
Yeah.
So you have no basic.
Well, that was my basis.
But they have guidelines like conservation of energy.
Yeah.
and things like that.
did you have records? You could access records?
Yeah,
public records?
and then every year I throw away the oldest year and add the new year.
Right.
So I'd adjust, okay? Didn't take much adjustment each year. Worked very well. All right.
You know what they say, don't you?
Huh?
If you're so smart, how come you're not rich?
You said I'm not rich. Okay. I'm doing this as a volunteer. I don't make any money here.
Wasn't that the Bernie Madoff defense too?
See me after class.
Have I got a deal for you?
Yeah. Okay, so let's, all right, early in the Manhattan Project, Fermi's attention was focused on the use of reactors to produce plutonium. In September of '44, he arrived at Los Alamos shortly after getting the Hanford reactor going, which of course is where they produced the plutonium. Oak Ridge was used for uranium. Soon after Fermi's arrival, Keller's superbomb group, of which Ulam was a part, was transferred to a new division headed by Fermi. Ulam, who was born in 1909, died in 1984, was a Polish scientist, studied math and nuclear physics, and originated the design. He also contributed to the concept of cellular automaton, and he invented the Monte Carlo method of computation along with von Neumann. Okay? So, this is also used in genotyping. I'll read this to you because it's hard to read. Many DNA samples found in criminal investigations contain DNA from several people. A number of computer programs seek to deconvolute these mixtures. That is, to infer the several DNA profiles that are meshed together in the electrophoretic data. The better ones do so using probability theory and an estimation procedure known as a Monte Carlo Markov chain. These programs are often said to perform probabilistic genotyping. Although both words in this name are a bit confusing, lawyers should appreciate that the inferred profiles are just possibilities, not certainties. At the same time, some may find the idea of using techniques borrowed from a gambling casino, in name at least, disturbing. Indeed, I've heard the concern that you know, don't you, that if the program is rerun, the results can be different, which is true whenever you're using random numbers. The answer is yes, that is the way the approximation works. Using more steps in the numerical process also could give different output, but would we expect the further computations to make much of a difference? The answer is no. Consider a physical system that computes the value of pi, like the program I wrote. I am thinking of Buffon's needle. In 1777, George Louis Leclerc, the Count of Buffon, imagined dropping a needle on a lined sheet of paper and determining the probability of the needle crossing one of the lines on the page. Okay? He found that the probability is directly related to pi. For example, if the length of the needle and the distance between the lines are identical, okay, 10 inches, okay, one can estimate pi as twice the number of drops divided by the number of hits. Repeating the needle dropping procedure the same number of times will rarely give exactly the same answer. Note that pooling the results for 2 runs of the procedure is equivalent to 1 run with twice as many needle drops. For a very large number of drops, however, the approximation should be pretty good, and it is. I ran this program doing exactly that. I ran it, 10 times, okay? And you can see that I never came up with exactly the value of pi, but I came pretty close. I didn't bother averaging these numbers, but I imagined that they would come out pretty close to 3.14. It works. Okay? So I basically dropped a needle on a sheet of paper, simulated this, okay? I didn't do it actually. I simulated it on the computer. I had 2 lines on the paper, and every time the needle crossed the line, I counted that as a hit. But if the needle fell in such a way that it didn't cross the line, that was a miss. And then I did the calculation that was described, and I came up with a value for pi that's pretty close. It works. These computations are more complicated. They simulate a random walk that samples values of a random variable to ascertain a posterior probability distribution. The walk could get stuck for a long time in a particular region, but the general approach is very well established in statistics, and Monte Carlo methods are widely used throughout the sciences. The book Dark Sun, The Making of the Hydrogen Bomb, again by Richard Rhodes, who also wrote The Making of the Atomic Bomb, okay, provides the following account. On leave from the university, resting at home during his extended recovery from a severe brain infection, Ulam amazed himself playing solitaire. Sensitivity to patterns was part of his gift. He realized that he could estimate how a game would turn out if he laid down a few trial cards and then noted what proportion of his tries were successful, rather than attempting to work out all the possible combinations in his head. It occurred to me then, he remembers, that this could be equally true of all processes involving branching of events. Fission, with an exponential speed of reactions, was a branching process. So would the propagation of thermonuclear burning be. At each stage of the fission process, there are many possibilities determining the fate of the neutron. It can scatter at one angle, change its velocity, be absorbed, or produce more neutrons by a fission of the target nucleus, and so on. Instead of trying to derive the expected outcomes of these processes with complex mathematics, Ulam saw, it should be possible to follow a few thousand individual sample particles, selecting a range for each particle's fate at each step of the way by throwing in a random number and taking the outcomes as an approximate answer, a useful estimate. This iterative process was something a computer could do. When he told von Neumann about his solitaire discovery, the Hungarian mathematician was immediately interested in what he called a statistical approach that was very well suited to a digital treatment. The 2 friends developed the mathematics together and named the procedure the Monte Carlo method, for the element of chance it incorporated. Even without a computer in place, the Los Alamos staff, including a bevy of young women who had been hastily recruited to grind manually on electric calculators, performed preliminary calculations examining the feasibility of igniting a thermonuclear reaction. I gotta mention another use of this as well. There's a branch of calculus called integral calculus. Integral calculus is used to find the area under a curve. So if you know the formula for the curve, you can find the area under the curve. It's very useful. Many, many different applications. I wrote a program that had a square, and inside the square there was a circle. Okay? Now the radius of the circle was known. Okay? Say it's 1. All right? If the radius is 1, the area of the circle is pi. Okay? Because pi r squared is pi times 1, which is pi. I threw random numbers at the square. The guarantee was that each random number, the coordinates for each number, each point, would be within the square. And I counted the percentage of those that fell within the circle. And sure enough, came up with the value of pi.
That is the program you showed. You didn't supply the explanation at the time, but
Yeah.
that was what you showed.
Okay, that's what I was doing, yeah. I was throwing random numbers at a square. Should I go back to that?
Well, that makes more sense now.
Yeah. Which one was that? The first one, what, this one? Okay, so, yeah, that's what I was doing, so.
Lines 50 and 60 are selecting.
So here, I made the radius is 10, okay? The radius is 10. So the center, yeah, the center of the circle, the x and y coordinates are 10 and 10. Yeah. I can't remember what I did, but I'll figure it out.
Well, the coordinates were set.
Be patient. We'll be out of here by
Zero
noon.
and 20, so it's a line on the square.
So then I go into a loop, okay? I'm gonna do this 1,000 times, all right? 1,000 times. So I said x is a random number times 20, y times 20. Well, because the maximum value for x is 20, right? That's the length, the width, let's say, of the square.
So now the random numbers are between 0 and 1, is that right?
Random numbers between 0 and 1, right? So for x, the number 50 there is just a line number, okay? So ignore that. X is random 1 times 20, which means it's a value between 0 and 20, okay? But not including 20, okay? The y coordinate is also between 0 and 20. Then I calculate the distance from this random point to the center of the circle to see if it's within the circle. Okay? If the distance is greater than or equal to 10, then I don't count. I skip the next line. I go down here, and I only count that as part of the total number of hits, of tests. But if it's less than 10, then it's within the circle. So I count it as a hit. Then I just take the ratio of the hits to the total number of points, okay? And come up with this. Make sense? So I'm just, it's like throwing darts at a dartboard, okay? And on the dartboard is square, and there's a circle inside the square. Okay? I throw darts at random, with the only requirement is that each dart has to hit the board. And then I just count the percentage of darts that fall in the circle, divide that by the total number of darts, and I get, for a circle with a radius of 1, I get pi. I get the area of the circle, in other words.
So how did this work with with the cards, and he said he had a deck of cards and he would play solitaire?
He would deal certain cards out initially, okay? And then he would say, did I win that game or didn't I? Did I get a hit or didn't I?
All right.
And he was able to figure out right away. But what that led to was the important thing. You got all this nuclear fuel and all these possible reactions. What if 10% goes here, 15% goes here? What's going to happen? And they were able to figure out the percentages that would give the greatest yield.
Did Las Vegas blacklist the staff of Los Alamos for people like that?
Very possibly. Yeah, very possibly.
Well, actually, Las Vegas wasn't around then. In the 50s.
No, it's Monte Carlo.
Well.
That's where the
this in
casino
the
was.
40s,
Yeah.
I recall.
That's why, otherwise they might have called it the Las Vegas. But Monte Carlo is where the
Maybe they
casinos were.
started Las Vegas.
Yeah,
Monte Carlo is
Oh, what happened?
incredible.
I have to go through the whole thing now. I went too far. Okay, I don't know what happened. Let's see.
Went critical.
Almost to the end.
Okay, Azulim recalled, and this is a quote from him. We started work each day for 4 to 6 hours with slide rule, pencil, and paper, making frequent quantitative guesses. Guesses, random numbers. These estimates were interspersed with stepwise calculations of the behavior of the actual motions of particles. What you were talking about, Steve. The real times for the individual computational steps were short, and the subdivisions of the materials assembly very small. The number of individual computational steps was therefore very large. We filled page upon page with calculations, much of it done by a man named Cornelius Everett. In the process, he almost wore out his own slide rule. I don't know how many man-hours were spent on this problem. Okay. So in summary, everybody understand what the Monte Carlo method is now? Okay? Just take these random numbers, plug them in, and see how many hits you get, basically. And then you take that as a percentage of the total number of tries. So in dealing cards, he would have certain cards out there, they were the hits. And then he'd see if he won the game. And so if he did, then that combination produced a hit. If he didn't win the game, then it was just another trial.
Is that what casinos do?
You would play the game using the same cards initially in order to establish what the chances were of winning with that configuration.
Well, and then he randomly changed the number of cards, yeah.
Oh,
It changed the remaining
The
cards.
remaining cards.
He was trying to assess what the chances were of winning a game,
Right.
just given the initial cards.
Right,
It would save so much time if you could do that.
yeah.
Is that what the casinos are doing, how they figure and calculate to get themselves ready?
No, they just rig the game so they can't lose.
So it's even worse than that.
Yeah.
so this was a game of solitaire?
Yeah, solitaire, yeah. That's what led him to it, but because he was sick and he had nothing else to do, I guess they didn't have TV, so he played solitaire. Yeah. In summary then, okay, so everybody understands the Monte Carlo method, right? Very simple, really, and very effective, and used in a wide variety of economics, biology, medicine, criminology, and of course physics. So in summary, the hydrogen bomb is significantly more powerful than the atomic bomb due primarily to the abundance of available fuel, lithium deuteride, which is very easy to handle, right? It's not radioactive, you know, it's just there, okay? Very easy. The hydrogen bomb depends on a fission igniter. The development of the hydrogen bomb depended on using the Monte Carlo method to investigate combinations of variables that would result in the desired explosion. Teller's perseverance, with Ulam's help, is credited for the successful development of the hydrogen bomb. Oh, here's the map that I wanted to show you before. So you can see that a hydrogen bomb would encompass most of England, okay, parts of Belgium, France, Paris is right here. Yeah, this was exploding in London, okay? So London, the destruction of London would destroy Paris, and as far north it looks at something, Liverpool maybe? I don't know, there's Liverpool.
What size bomb is that?
Scotland.
It would pretty well wipe out the England. It would
What
wipe out
size
England.
bomb is that?
Is that
Pardon?
showing Brexit?
What size bomb is that?
That's a good question. I don't know. I'll try to look that up. Yeah. Any questions, comments?
I
Yes,
saw
sir.
one of those maps based on the United States. If the bomb was dropped in Baltimore, and I think it was 100 megaton, it would literally wipe out Boston all the way down to beyond Richmond. And it would be Philadelphia, Washington, Baltimore. It's amazing.
Yeah, yeah. It's scary. And I don't know how many hydrogen bombs we have, but it's more than one, I'm sure. Yes. Thank you very much. See you next week. Maria Meyer.
There's something I heard about Teller, how he was reputed to be the father of the hydrogen bomb because of all his work
Right.
pushing it. But the joke is that really Ulam was, because he came up with the idea of it detonating the atomic bomb outside the fusion bomb structure,
Right.
so that it wouldn't get blown apart. That's the problem they were unable to solve.
Yeah, and Teller resisted crediting Ulam with anything, but the eventual structure is called the Teller-Ulam
Well,
structure.
Ulam just came up with this idea, so the suggestion is really he should be called the father of the hydrogen bomb because his contribution was made in moments.
Yeah,
It was Teller that had to carry the project for months.
right.
Suppose they apply this Monte Carlo approach to, to global warming and trying to limit that, or peace, how countries could work, cooperate
Oh, they
together.
do. Oh, yeah, I didn't mention that, but there are, I mean, they play war games like that. That's exactly how they do it. They say, what if this happens and this happens to this extent, or at this time frame, or with these results, what's going to happen? And they run it over and over again and look at all possible scenarios. And the more they run it, the more it tends to produce the same result, and that's what they come up with. Say, this is the most likely thing that's going to happen.
Astronomers run a lot of Monte Carlo models.
Oh, yeah. Modeling stars.
So that's the amazing effectiveness of mathematics.
Yeah.
Yeah, when we were showing earlier the slides of the fusion reactions, it involved tritium, but tritium is artificial and it breaks down. It's not a stable isotope of hydrogen. So if you have that in a hydrogen bomb,
No, it's produced by the fission. That's the key.
oh,
Yeah, you don't have to load tritium in. You only need the deuterium, and deuterium is not radioactive,
okay.
so you don't have a problem. Not strongly radioactive.
Just,
How is the radioactivity of a hydrogen bomb? Is it as bad as a regular atomic bomb?
Well, no. In fact, it has very little. But the uranium, the plutonium in the bomb is what is the problem.
But there's less of it in the hydrogen bomb, isn't there?
Yeah.
Okay.
like most of you here, I visited Hiroshima and went through the museum, and there was shadows that had been burned into the stone.
Yeah.
They were so high.
Yeah, from the light.
Oh,
The light was so strong that if you looked at it directly, you'd be blinded. And even if you didn't look at it directly, it could burn you. And it was so strong that it did cast shadows. Well, it burned the concrete, it bleached the concrete around the shadow. So you ended up with a shadow of the person that was standing there, yeah. Yeah, my daughter went to Hiroshima and sent us a picture postcard of the one building that's left standing as a reminder of what happened, yeah. It's just a shell of a building, yeah. Thank you very much, see you next week. Maria Meyer.